Earth holds about 1.386 billion cubic kilometers of water, but about 96.5% of it is in the oceans. Only around 2.5% is freshwater, and most of that is not easily accessible. Nearly 69% is locked in glaciers and ice caps, while about 30% is stored underground. The fresh water in rivers and lakes, the sources that supply much of the water people use every day, accounts for only about 0.007% of all the water on Earth. As populations grow and freshwater supplies come under increasing pressure, many water-stressed coastal regions are turning to the one source that is almost impossible to exhaust: seawater. So, how does a desalination plant turn seawater into drinking water? How can it remove dissolved salt from millions of liters of water every day? And once the fresh water has been separated, what happens to the concentrated seawater left behind? The process begins with bringing seawater into the plant. Before any salt can be removed, the plant first needs a constant supply of seawater. In many coastal plants, large intake pipes extend offshore and draw seawater toward the treatment facility. At the entrance, screens stop larger debris, seaweed and marine animals from entering the system. The intake velocity also matters. If water is pulled in too quickly, fish and other organisms can be trapped against the screens or drawn into the plant. Some newer facilities use subsurface intakes, where seawater first moves through layers of sand or seabed material before reaching the intake pipes. This provides a degree of natural filtration, although the geology and coastline do not make this possible everywhere. Once the seawater reaches the plant, it is still nowhere near ready for desalination. Ocean water contains suspended sand, silt, microscopic organisms, organic material, and minerals. All of these can interfere with the equipment further downstream, particularly the reverse osmosis membranes. A layer of biological growth or mineral scale on a membrane makes it harder for water to pass through, increasing the pressure and energy required to keep the plant operating. So the first major stage is pretreatment. The exact process varies with local seawater conditions. Larger particles can be removed by conventional media filters, while some modern plants use microfiltration or ultrafiltration membranes to catch much smaller particles. Chemicals may also be added to help suspended material clump together, control microorganisms, or prevent minerals from forming scale later inside the reverse osmosis system. By the end of pretreatment, the water may look completely clean, but nearly all of the dissolved salt is still there. Removing that salt requires the most important part of the plant. For most modern seawater desalination plants, that process is reverse osmosis. The name comes from a natural process called osmosis. If fresh water and salt water are separated by a membrane that allows water to pass, but blocks most dissolved salts, water naturally moves toward the salter side. Reverse osmosis forces water to move in the opposite direction. High-pressure pumps raise the pressure of the pretreated seawater before sending it into long-pressure vessels containing reverse osmosis membranes. Seawater systems typically operate at roughly 55 to 82 bar, or around 800 to 1,200 pounds per square inch. That is dozens of times atmospheric pressure. Inside each pressure vessel are several cylindrical membrane elements. Instead of using one flat sheet, layers of membrane and flow channels are wound around a central collection tube. This creates a large membrane surface area inside a relatively compact cylinder. Pressurized seawater flows along one side of this membrane. Water passes through the membrane and moves toward the collection tube, while the vast majority of dissolved salts remain behind. Modern seawater RO membranes can reject more than 99% of many dissolved salts. But the system does not convert all of the incoming seawater into freshwater. Operational seawater RO plants commonly recover around 40 to 50% of the water entering the membrane system. If a plant operates at a 45% recovery rate, Producing 1 cubic meter of freshwater requires more than 2 cubic meters of seawater to enter the RO stage. The rest leaves as a concentrated saltwater stream known as brine. Trying to recover much more water makes the process increasingly difficult. As fresh water leaves through the membranes, the remaining stream becomes salter. Higher salinity means higher osmotic pressure, greater risk of mineral scaling, and more energy needed to continue forcing water through the membrane. Large desalination plants divide the flow across thousands of membrane elements arranged inside many pressure vessels. This modular design allows enormous volumes of seawater to be processed continuously, while sensors monitor pressure, flow, and water quality across different sections of the system. At this point, the plant has done what an ordinary filtration system cannot do. It has separated water from salts that were completely dissolved inside it. But maintaining those pressures continuously requires a great deal of electricity. And this is where modern desalination plants have made one of their biggest improvements. Reverse osmosis does not need to boil seawater, but it still has to overcome the natural osmotic pressure created by the dissolved salts. That makes the high-pressure pumps one of the largest energy consumers in the entire facility. When intake, treatment, desalination, and brine handling are included, seawater reverse osmosis typically requires around 2.5 to 6 kilowatt-hours of electricity for every cubic meter of freshwater produced, with efficient modern plants operating toward the lower end of that range. For a plant producing hundreds of thousands of cubic meters every day, even a small improvement in energy consumption becomes significant. The obvious place to recover some of that energy is the brine. After passing through the membranes, the concentrated seawater has lost part of its pressure, but it can still leave the RO vessels at dozens of bar. Simply releasing that pressure would throw away much of the energy that the pumps had just put into the water. Modern plants therefore send the pressurized brine through an energy recovery device. The main pump then only has to provide the remaining pressure required by the process. At Dua's Jebel Ali plant, the energy recovery devices are rated at about 96% efficiency, transferring pressure from the RO reject stream back into the incoming feedwater. This does not mean the plant recovers 96% of all the electricity it consumes. But without this recovery step, modern seawater reverse osmosis would consume substantially more electricity. Once the water has crossed the RO membrane, however, producing low salinity water is only part of the job. It still has to be turned into water that can safely travel through a city's pipes. Reverse osmosis removes not only salt, but also much of the calcium, magnesium, and other dissolved material that was originally present in the water. The resulting water is extremely low in minerals. That sounds desirable, but water in this condition is not normally sent directly into a municipal distribution system. Its chemistry has to be stabilized first. The plant therefore moves into post-treatment. Depending on the facility, calcium and alkalinity can be restored by passing the water through limestone or by adding carefully controlled mineral compounds. The pH is adjusted so the finished water is less corrosive to pipes and storage systems, and disinfectants are added to control microorganisms as the water moves through the distribution network. The finished water is continuously monitored before it leaves the plant. Instruments can detect changes in salinity and conductivity almost immediately, while additional tests check chemical and microbiological quality. Once it meets the required standard, the water can be pumped into storage reservoirs or directly into a larger municipal network. In some systems, desalinated water is blended with water from reservoirs, groundwater, or conventional treatment plants before reaching consumers. For the freshwater stream, the process is now complete, but a second stream has been moving through the plant at the same time. It contains almost everything the membranes removed. If a seawater RO plant operates at around 50% recovery, approximately half of the incoming water becomes freshwater, and the other half leaves the membrane system as brine. Because most of the salt remains in that smaller volume of water, its salinity can approach roughly twice that of the original seawater. With feedwater around 35,000 milligrams per liter of dissolved salts, a system operating near 50% recovery can produce brine approaching 70,000 milligrams per liter. For coastal plants, the most common destination for this brine is back to the ocean. But releasing a dense stream of concentrated seawater from one pipe can create an area of unusually high salinity near the seabed. That means the outfall is another engineered part of the desalination system, rather than simply a drain. Many plants use offshore pipelines ending in multi-port diffusers. Instead of releasing all the brine from a single opening, the diffuser sends it through several smaller outlets at relatively high velocity. This pulls surrounding seawater into the plume and mixes the two streams much more rapidly. California water authorities, for example, identify multi-port diffusers as a preferred method for dispersing dense brine discharges from new facilities where raw brine is released to the ocean. The design depends heavily on the location. Engineers have to consider water depth, currents, waves, seabed conditions, and the volume of brine being discharged. The goal is to bring salinity back toward the surrounding ocean level within a defined mixing zone rather than allowing concentrated water to collect near the bottom. Once that happens, the process is complete. One part of the original seawater has entered the city water supply, while the other carries most of its original salt back to the ocean. And that is how a desalination plant turns seawater into freshwater. Thanks for watching. If you enjoyed this video, please consider liking it and subscribing to the channel. And if there is another system you would like to see explained, let me know in the comments. Have a nice day.